Our next speaker is Kate Holman from Towson University. She's been working with my departmental colleague Chris Fink this summer, and she'll be discussing shaking up our understanding of epilepsy.
Hi, my name is Kate Holman. I'd just like to start off by thanking the National Science Foundation for funding me, Ohio Wesleyan University for hosting all of us this summer, and my mentor, Dr. Fink, for teaching me everything I've learned. So 1.8% of adults worldwide have epilepsy. Some people, like my mother, choose to manage it with diet and lifestyle choices. Other people manage their epilepsy with medication, and still yet others manage it through brain surgery. So if you're sitting in the operating room, how does your neurosurgeon know where your seizures are happening, what kind of seizures you're having, and most importantly, how do they make sure they don't remove the wrong part of your brain? The most powerful tool that current neuroscience has for collecting data to answer these questions is measuring the local field potential. And here you'll see devices for measuring the local field potential. It's just like EEG, but they stick the electrode inside your brain. They have to crack open your skull first. So what is local field potential? If you shrunk yourself down to the size of a very, very tiny electrode and we're looking at one single neuron, what would you see? You would see ions flowing in through the soma of the cell, down the axon and out of the axon terminals as an electrical signal passes through. And if you came back to normal human size, you could approximate this one single neuron as a dipole with the negative pole at the soma and the positive pole at the axon terminals. And if you were to plot the potential as a function of time, this is what it would look like for one neuron to send a signal and for one neuron to receive a signal. But of course, with local field potential, the electrodes we're using to measure are not that tiny. Local field potential is the measurement of many neurons that surround the electrode you're using to measure. So like a cluster of neurons within your brain, just a whole group of them. All right, so it's been common knowledge in neuroscience for the last several decades that seizures are the result of hypersynchronous neuronal firing. Just everything is very highly synced, everything's firing at the same time. And this is true in many seizures. As you can see in this human seizure data, the local field potential is traced at the top. And then at the bottom, you have a raster plot of all the neurons that the local field potential is being measured from. So this just assigns an arbitrary ID number to every neuron because we have to plot them somehow, even though it doesn't matter how we plot them. And then it plots it against time, and every single time one of the neurons fire, we just put down a black dot. And you can see that the strong oscillations in the local field potential during the seizure are very clearly due to the neuron firing. And that all the neurons are firing at the same time. However, there's been recent data published that has recorded human seizures that are the result of asynchronous neuron firing. And this is that data. So you have a local field potential that looks different because it's a different type of seizure, but you also still see very strong rhythms, strong oscillations in that local field potential. And the big question is, why are we still getting these strong rhythms in the local field potential? Why doesn't this recording of this seizure just look like noise? And Dr. Fink has a hypothesis for that. So he hypothesizes that strong rhythms in the local field potential can emerge from asynchronous neural firing when all the neurons are firing asynchronously, but with approximately the same frequency. And this is a color plot from his paper published in June that shows a computational simulation of asynchronous neurons. And you see a narrow band emerge. The strong rhythms emerge at a frequency of about 200 hertz, which is very encouraging. And then every now and then you'll see a doubling of the frequency, and you'll even get a first harmonic. But most importantly, he's shown that computationally, we can get what we're seeing experimentally. So my research question, what my research has explored this summer, is looking at how much heterogeneity a cluster of neurons can tolerate and still produce strong rhythms in the local field potential. So asynchrony versus heterogeneity is kind of a fine point. Asynchrony tells you that the neurons are firing at different times, and that's all it tells you. Heterogeneity says how they're firing at these different times. And my computational model has two types of heterogeneity in it. The first, which I call sigma ISI, is variation in the frequency. And the second type of heterogeneity, which I call jitter, is variation in the spike timing. And here's a nice visual model of that first type of heterogeneity. So sigma ISI changes from one neuron to the next neuron. So you say your system has an average frequency, but each given neuron may not have that exact frequency. You average over the whole network and you'll get it, but from one to the next it's going to be approximate. And we choose these frequencies by drawing from a Gaussian probability distribution where the frequency for the entire system is the mean value, and we change the spread from one neuron to the next by controlling the standard deviation. Then jitter is the change in intrinsic or in interspike interval from one event to the next. So if you see, this is all neuron 3 from the last slide. The top has no jitter at all. It's exactly the same. Every interspike interval is consistent. The middle one is mid amount of jitter, or it's a low amount of jitter, maybe like 10 to 15% jitter. And then the bottom neuron, or the bottom segment of time, has a large amount of jitter, maybe 40 to 45%. And this spread we also control using another Gaussian probability distribution. So what does all this data look like when we simulate it? This is an example of low heterogeneity in a system. At the top you have the local field potential, the trace, and then at the bottom you have the power spectral density plot, which is just the local field potential run through a fast Fourier transform so you can look at the discrete frequency components. And we have a very strong rhythm at these low levels of heterogeneity, as you can see with the strong peak at the fundamental frequency of 25 hertz. And then you also see the occasional doubling of frequency at this low heterogeneity with that first harmonic in there at 50 hertz. And what does a high level of heterogeneity look like? So this would be 50% jitter, 50% ISI, and as you can see, the strong rhythms, the oscillations in the local field potential are no longer present, they look different. And the peak at 25 hertz, the fundamental frequency, the mean frequency for the whole system, is no longer as strong. You have a bunch of noise at the beginning that's just due to the type of waveform used in this data. So how do we quantify the strength of the oscillations from one set of data to the next? So from 5% to 50%, it's very clear that one has a stronger rhythm than the other. But how do we do from 5% to 10% or 10 to 15? It gets a little trickier. We've devised a signal-to-noise measure to quantify this that just takes the peak, the maximum value from the fundamental frequency that we're looking at, and compares it as a ratio to the levels of noise at the higher frequencies. And if you recall, this is 5% jitter, 5% sigma ISI. That was the very first piece of data you saw. And then that was the very noisy piece of data you saw at the end. And we've done this for many, many different frequencies. And what we concluded is that you can have strong rhythms in your local field potential emerge with a maximum of 20% combined heterogeneity. So between the jitter and between the ISI, you can have 20% combined and reliably get that strong rhythm emerging in your local field potential during a simulation of a seizure. All right, and we just wanted to double check our data to make sure we were really working with asynchronous systems, because that's kind of what the whole underpinning of this project is relying on. Synchronous systems, whatever, people have been dealing with that for decades. And we found out, no, we're not secretly synchronous, and we just used a standard synchrony measure in the field and analyzed all of our data. if you didn't understand a single other word I said, these are your 2 points. First, seizures can exhibit strong rhythms even with asynchronous neural activity. And this is the big finding in the field and what made us want to investigate what we're investigating. And then the second point is what we've concluded from our work in our lab is that asynchronous networks can produce those strong rhythms with up to the 20% combined heterogeneity in the neuronal spike timing. Okay, any questions?
Thank you, Kate. Questions?
So, a difference between, okay, so when somebody has a seizure from the neurons, being synchronous or asynchronous, is the seizure like worse or less bad or something if it's like more synchronous or more asynchronous? Does that impact it?
So seizures are kind of like cancer. There are a million different kinds, and they all affect everyone's body differently. So people may experience all synchronous seizures, they may experience all asynchronous seizures, and depending on the type of seizure you're having, that's going to make you feel like, worse or not as worse. I don't know if there's like quantifiably, yes, asynchronous seizures are always worse. I think it's just, it depends on the person and how it affects their body.
Do you have an idea from any experiments, like how much jitter you might expect to see between cells and
No, we don't.
cells?
No, we just know that there normally is jitter present, that you can't expect cells in the brain to just fire like clockwork.
Right.
Any other questions? All right, let's thank Kate again.